Hello, good morning, everyone. First, I want to make a couple of announcements. Let's go to our course website on Canvas. You can see there's some tutoring information posted. Now, we offer tutor from our learning assistant that are physics majors, undergrad students. So they host some Zoom office hours online. So you can check this announcement. The second listed here, and the very first listed here are the tutoring offered by the university, the Learning Resource Center. So they have every Friday that you can walk in. It's a happy hour tutoring session. You don't need any appointments. So the link is on their website. Also, I had previously posted a happy hour information here, so you can find their Zoom link. On top of that, they have you can make an appointment for one-on-one, and you can select get assistance from the website SCPP Connect. Okay, so just follow the steps and you'll be able to find the tutor information. Also, I want to make a quick announcement about the partial credit. Some of you were not here on Friday, so I wanted to make sure everybody is aware of that. So read the detailed information that I posted on the modules to look for information about how to get this partial credit. Okay, and if you have any questions, feel free to let me know. All right, so now I'm going to switch to our class. One second. Okay, so it's just taking a little bit for the screen to show up. All right, so we have talked about work done by a variety of forces. So gravity does not depend on the path. It only depended on the vertical distance. So we talked about that. MGH, the work done by gravity, is either positive or negative MGH, depending on you're going up or going down. The work done by kinetic friction is always negative because kinetic friction always opposing the direction of travel. And that does depend on the path. So if you follow a longer path to a destination, it will be more, in terms of absolute value, more work done by the kinetic friction. We also showed an example that it is possible for static friction to do work. Now let's look at this particular bridge question that you have already done. It has to do possible work done by other forces. Now there's three different scenarios. One is just an object falling, free fall. Now we know that the only force on it, it's gravity. So the only work is also gravity, MGH, during that process. The second is this little object going down the ramp. So you know, it's a frictionless incline plane. It's a ramp, so you have normal force. So let's take a look at that. So from going here to here, going down, do you think normal force do any work on the object? Does normal force do any work?
No.
It doesn't, right? And how do we know that?
Is it because it's frictionless?
It's frictionless, yes. So we know that there isn't any friction. So you can say there would not be any work output, energy loss due to friction. That we know. But does normal force do any work? So to think about whether you have work or not, we always go to what? We always go to the definition. You want to look at this force and the displacement. Which direction is a displacement? It's going from where you are to where you were to where you are. So the displacement vector is delta R is along the ramp pointing down, and normal force is perpendicular to the ramp. So look at these two vectors. If I calculate the work done by normal force, what would I get? I would get 0. Very good, Jacob. Thank you. Because it has a 90-degree angle between these two forces, right? They are these two vectors, they're perpendicular. All right, so normal force doesn't do work. And in this case, the third case is a string. We have sort of a pendulum, right? So tension, this is the tension in the string. It's always pointing along the rope, obviously. Does tension do any work in this case? You can think about if that force do work, you need a displacement in the direction of the force. And that's another way to look at dot product. Is this displacement in the direction of the force? This third scenario. Does strain do any work? All right, I see some shaking head. And do all others, do you agree? Tension doesn't do any work? Now you might be tempted to say, no, how do we convince other people? You want to show, okay, previously you showed that these two forces, the force and displacement are perpendicular to each other. So if I can show also my displacement is perpendicular to my tension, I can be convinced it has to work. Well, the displacement for this is, you can see at every, it's not in a different time intervals at a different time, it's at different directions. But I know my velocity is always tangential, right, to my curve, to the path. So if you're looking at a displacement that's between 2 times as super close to each other, from this moment to right, in the next moment, this is also your direction of your displacement. So you can see that no matter which instant you look at it, the tension is always perpendicular to your displacement vector along the path. So overall, again, there's no work done. So no work done by tension, and there's no work done by normal force. But obviously, there is cases where tension could work. You can simply just drag an object along. But in the case of a pendulum, there is no work done. Okay, so it turned out for all these different scenarios, the only work done on it that's not 0 is the work done by gravity. Okay, so that's one thing we wanted to talk about. So we have looked at different scenarios that work done by different objects. There is one more definition that's simply using the total work done by the total time it took. It's called the power. Power is at what rate the work is done. A really quick analogy for that is you can go walk upstairs or you can run upstairs. So in terms of how much work is done, it's the same. It has achieved the same effect. You have went up 15 flights of stairs, but obviously you need a much bigger power if you're running, right? Because all that work is done in the much shorter amount of time. So we defined the average power to be the total work divided by how much time it takes to do that work. And the instantaneous power is the derivative of dw over dt. Simply, if you're looking at a instant, because you can have a bigger power now, but then a smaller power later. So at any instant is derivative of dw dt. So that's just one extra little concept. Now we talk about power in our daily language a lot, right? We say we talk about the power of our electric appliances. You can have a microwave that has a higher power. Now, what does that mean? So if you have, now we talk about watts. 1 watts is the SI unit for power. So you may have 1100 watts microwave, or you have an 800 watts microwave, for example. Now, if you use the same microwave to heat up food, which one is going to take more time? The 1100 watts or the 800 watts? Which one will take more time to cook the same kind of food?
The 100 watts.
800, yeah. The smaller the power, the longer the time it takes, because eventually you want to be able to do the same amount of work. And then when we talk about heating up food, we're talking about the energy, right? You need to transfer energy, how much energy is being transferred. So to transfer the same amount of energy with a smaller power, you need more time. So this concept should be easier to grasp because we really use it and also use it in a proper way in our life. Now, if you see a different unit, it's okay. You simply will just look up the conversion. For example, horsepower is also just a different unit for power, and then we can just look up the different unit conversion to convert to the SI unit. Okay, so this is just sort of a side concept. But all the purpose of doing work, why do we want to study work? Because we want to be able to calculate the energy transfers, either as an input or as an output. So finally, we have done work. We need to put it back into our energy equation to solve more problems. Okay, so we'll try to do more problems today. I have 3, and for each of the 3, we wanted to use 2 different kind of choice of system, but we may not be able to finish all 3. So if we can do 2, and then you can do it by yourself, the other one, that would be pretty good. Okay, so energy inputs or outputs. Sometimes you have work, positive work or negative work. Okay, so we will identify whether this work will become an energy input, and then we use the absolute value of that work. Or is it energy output? We get, again, we will put in here as the absolute value of the work into the inputs and outputs. Okay, so when we talk about inputs and outputs, they are all positive. We take care of the sign by putting a negative sign in front of the output. Okay, so once you calculate work, and then you will use the absolute value of that work and plug it into the energy equation. Either put it as input or as an output. We'll start with this first example. All right, so we have a little puck, and since this is a frozen surface, what this is telling us, we don't have to think about friction. Okay, so this will do not have to think about friction. With an initial velocity 4 meters per second, it slides up a hill, and it's trying to slide up a hill of 1 meter height. Now the question is, will the puck make it all the way up the ramp? Will it be able to go all the way up? So this is a question we can easily solve with conservation of energy. Now, if you were to do Newtonian mechanics with Newton's laws, it will take a little bit longer. Actually, you can still solve it, but a little bit longer. Okay, we will simply use G as 10 meters per second squared. Okay, so this is our question. Okay, take a screenshot and we will refer back to it later. Okay, I'll pause for a few seconds and I'll move on to the next slide. Okay. All right, so now let's try to solve it. We will use different choice of systems. I want to show you have total freedom to choose whichever system you like. But obviously you have to choose puck to be your system because the question is about the puck. If you choose my chair, well, it's not so interesting. That's not going to help with this problem. So you have to choose the puck. But on top of that, whether you include the earth or not is totally up to you. Okay, so you have 2 different choices, either system 1 or system 2. And what the problem is asking is, well, what is the highest that the puck could go? So let's say with 4 meters per second, it can only go up as high as 80 centimeters, for example. Then you can go back to look at this question saying, well, if the highest it can go is 80 centimeters, that's less than a meter, it's gonna go like a little over halfway, and then it's gonna slide back because it cannot go any further. And then we will say, well, the puck did not make it all the way up the ramp, right? So the question is, what is the highest point the puck could go? So that sort of interpreted the original question to another question. What is the highest point the object could go? So we wanted to calculate h. So that's our goal. So the next, before we solve it, the hard part is figuring out each of these energy terms, because once you figure it out, plug it into that equation is easy. So this is for you guys to work out. Okay, so now if you start with puck and earth as your system, what are all these terms should be respectively? Final energy, initial energy, energy input, and energy output. Okay. All right, so make sure you record all these different answer choices, take a screenshot, and we will have a discussion for a couple minutes, and then we'll come back to solve this problem together. Okay. All right. We will run the clock for 10 more seconds. So if you haven't voted already, please do so. All right. Any more votes before I close? All right. Okay. Let's take a look. We have a majority votes for A. Okay, slightly much less for B and C. All right. So let's take a look at this together. All right, we included Earth in our system. Very good, which means we can talk about potential energy. All right, so final moment is when the puck is up high. Initial moment when the puck is over here. Okay, I agree with your choices. Now, finally, you're here, then you have potential energy. Initially, you have kinetic energy because you're moving, and there's no energy input, and the energy output is work done by gravity. That's choice A. So what do you think about this? What do you think about the last term, work done by gravity? Should we list that as a energy output? If we had chose puck and Earth to be our system?
No, because it's not out of the system.
Grant said, because gravity is now not an external force, right? So is that what you mean?
Yeah, that's what I mean.
Yes, very good. Gravity is now part of the force in between your system. Earth is now included. So you cannot include the work done by gravity. So what do we say? We say you either have potential energy or you have work done by gravity. Either or, you cannot have both of them to show up in the same equation, okay? You have chosen Earth to be in your system, you have potential energy. That's what you chose. But if you include the Earth in your system, you should not have work done by gravity because gravity now does not do work on your system because Earth is part of your system. So what we need to do is to swap out this term to be zero. So C is actually correct for this particular choice. Okay, we can look at, let's solve this problem together. So now we have listed all the energy terms. We're now ready to solve the problem together. So remember, for every type of problem, we have an approach. We always start with drawing a picture, right? With kinematics, we draw a picture to show the motion. With dynamics, we also draw an object, and then we draw the free body diagram that's particularly useful for Newton's law problems. Here for energy, conservation of energy problems, other than these two steps, which is you always do, drawing a picture and decide on what questions you want to solve. In this case, is the highest point H. You will start with choose a system after you've done these previous steps for all kinds of problems. For conservation of energy problems, you always need to be explicit about your system. And we did. We say puck and Earth is our system. And we need to define what is initial and what is final. You did that as well. We said initial when the puck is at the bottom. It start to slide. And the final moment when the puck is at its highest point. And is it obvious why we chose these two different moments? Because we know some information about initially what's happening. It's with that velocity, we want to know what's going on finally. So that's why we identified these two different moments. And the third step is to find all these energy terms. And we also did that And then the fourth step is to put it together. So the final, you said it's potential energy. So that potential energy is what? M of the puck, G gravitational acceleration times the highest height H. And we don't know what it is, right? So it's mgh for the final energy. Initial energy of the puck is kinetic energy as you specified. So kinetic energy is 1/2 mv squared. Okay. Energy input is 0. Now the puck, there's no other forces making it speed up. And Earth is already included. Okay. So right now here you should put 0. So now we are ready to solve the problem. Now the final step is to put everything into your energy equations and you can solve it. So let's see what the final answer is. If I put, okay, mgh as my final, 1/2 mv squared as my initial is equal to 0 minus 0 is 0. I can solve for the height. I can cancel my mass actually. I can solve for the height to be v squared over 2g. Okay. You can plug in your numbers. So v is the initial velocity is 4 meters per second. G we had used 10, and this is to be 0.8 meters. So so here we're almost done. You just need to go back to the original question. Well, since this 0.8 meters is less than 1 meter, then the puck did not make it up the ramp. Okay, so it kind of slide halfway and then it goes back down. Any questions about how we solved this problem here? Any questions? Does that look all clear? Good. All right, now I'm going to ask us to switch the choice. Now we use puck as our system. Earth is not included, So think about, okay, now which of these answers are correct for our energy terms? Because once you use a different system to solve the same problem again, you should get the same answer. We want to be able to see, do we indeed get the same answer, okay? Again, you can take a screenshot and we will have a discussion about this particular system choice and then see how we can solve that. We'll discuss that for about a couple minutes, okay?
Professor, for this one, would there be a difference or would it be C again since we're trying to get the same answer?
We're trying to get the same final answer, but we're not trying to get the energy terms. Actually, they will not be the same.
Okay.
Yeah. I see that you have a discussion, something being 0. You're thinking B, right? Do you all agree? You all agree it's B?
Yeah, I think it's B.
Okay, yes. The energy terms, kinetic energy stay the same, but you don't have potential energy anymore because you have not included Earth. But now you do have to think about work done by gravity, and that is an energy output. Very good. Does that make sense that work done by gravity is an energy output? And why do you think that is an energy output, not an input? Yes, gravity is the external force, and this force could make the system, here the puck. Now the work could be giving in more energy to the system as an input, or could be taking energy out of the system. So how do we know work done by gravity is now an energy output, but not an input? So if the energy of the system is only kinetic energy, if it's losing that kinetic energy, then you would say, well, there must be an energy output because that's going away, right? So is that the case here, that our object is losing its kinetic energy?
Yes.
Yes, because it is slowing down. Very good. So we know that gravity is now an energy output. So if you had switch out these two terms and then have that as an answer choice, then that would be a wrong choice. Very good job, everyone. Thank you for participating. I will see you shortly when we go back to the main session. All right. Okay, so 10 more seconds for last minute vote. All right, let me go ahead and close it and we can take a look. All right, so pretty good consensus on choice B, where we do now have work done by gravity, and we're glad to see that. And we cannot talk about potential energy anymore, right? Because now Earth is not part of the system, and that energy is only belonging to the object and Earth system. So we don't have Earth, and we have no potential energy. Very good. So B is the correct answer. Good job. Now let's see if we really indeed get the same answer as before. So let's,
Professor. Oh,
yeah.
sorry, I was confused. Why would the input be 0?
The input be 0. Okay, so let's talk about why work done by gravity is an output. Anybody would like to defend the choice that the work done by gravity is an energy output, but not an energy input? Anyone?
Probably because we're kind of going from the kinetic energy to potential energy. I mean, to work, like the work, sorry. So that transference is kind of like going to its final form for the purposes of our problem.
Oh,
So that's why you can maybe think about it as an output.
okay, so yes, the kinetic energy is our only form of energy now. Your puck is your only choice of your system. For this puck system has only kinetic energy and finally has no energy. So from initial, you have some kinetic energy to final, you have 0 energy. During that process, you think that energy decreased, right? It's not increasing. So if there's work done, that must be taking that energy out of the system. So eventually it has some kinetic energy and then it has no energy. So that has to be an energy output because the puck is slowing down. The slow down eventually to a stop, right? So because of that reason, the work done by gravity is a energy output because it slowed the object down. It's not an input because there's nothing in there. There's no force there that to speed it up. There's no force there to increase the energy of the system. Does that make sense?
Okay, yeah, right.
Okay.
That makes more sense.
Very
Thank you.
good question because the inputs and outputs oftentimes we get confused of, okay, what is input and what is output? All right, work done by gravity. You know that the work done by gravity is always plus or minus mgh. Now, there is a little shortcut and trick is, well, since you're caring about the absolute value, you can just write mgh as a positive number. Because no matter if this work is negative or positive, you're using the absolute value anyway. Have you identified it already as an energy output? It turned out the work done by gravity, the object is going up and the gravity is pointing down is actually negative mgh, okay? But we are doing an absolute value of that. So you are going to use the positive mgh anyway, right? So to put everything together, let's see if we get the same result as before. Final is 0, initial is kinetic energy, inputs is 0, output is, we use this positive value, mgh. And what do we get? We get the same results as before. You can cancel the negative signs. You can also cancel the mass. Mass actually doesn't matter here. The highest point you can go is v squared over 2g, just like the one we got before, which is 80 centimeters. It can go up for 80 centimeters, 0.8 meters, which is less than 1 meter. So it cannot go up, not make it to the right. All right, you can see how the different system choices give you the same answer than they should, and how the mgh showed up in 2 different places, either as a potential energy or as a work done by gravity, but not both. Now, if you put both in there, you'll notice that your answer would be wrong. You would not get this correct answer, okay? All right, so that's an example to show you have the choice to choose whatever system you want, okay? You choose whatever system you want. Now, let's look at another problem. This one, we have the spring. So we haven't done the spring yet. So now let's do a spring problem. We will read the question together, okay? So at the train station, you notice that there is a very large horizontal spring at the end of the track so that when the train comes in, You have this safety device to stop the train in case, you know, the engineer misjudged the stopping distance. So you wonder, okay, what would be, so now let's give you what the question is. What would be the fastest train the spring could stop? So this is asking for an initial velocity, the fastest train that you can have for the spring to stop it safely when it's fully compressed at 3 feet. Okay. And now I'll tell you some information about the spring. So what kind of spring you have? The kind of spring that you have is the maximum stopping acceleration of the train, which is caused by the spring, because spring will exert a force, is g/2. Okay, when it's compressed for this much amount, it gives you that much acceleration. Now, this information is really just an extra sentence to tell you what the spring constant is. Okay, oftentimes when a complicated problem is no longer complicated if you can parse out what different parts is trying to tell you. So instead of telling you this, the spring constant is 450 newtons per meter, for example, it tells you some extra information you have to figure out yourself. Okay? But it's not complicating the process, as in if you know what it's trying to do. It's just telling you what the K is. Okay, so you make a guess what the mass of the train would be, and you decide to ignore friction for this particular estimate, okay? All right, so this looks like a complicated enough of a problem, more complicated than we would, the wording at least more complicated in our exam, but we want to be able to handle these kind of situations. So the first step is let's draw a picture to visualize the process. So, okay, I'm drawing, let's draw a train. Coming in with some velocity. And you need the train to stop the, you need the spring to stop the train. So, okay, so this is before, this is initial. It's just start to touch the spring, but it's not stopped yet. But then it is fully stopped. So the train must have gone forward a little bit more. So my picture is not very nice, but we just want to be able to tell what's going on. So this is our initial. Okay, this is our final. And you can see that, well, from just touching the spring to the spring being fully compressed, they tell us delta x is what? Delta x is 3 feet. Okay, so this is a picture I draw. What else information I can put on it? Okay, the mass, I didn't put it on it yet. I could say, okay, 0.5 million kilograms. And also telling us at this moment, I have an acceleration that is g/2. So I have put all the information is given to me and put it on my graph. All right, so let's not worry about the spring constant at this point. We'll figure that out later. But now let's think about, okay, qualitatively what this problem is about. It's about an initial moment with some velocity, and the final moment is there's 0 velocity, the train stopped, but the spring is compressed, and we wanted to find out, the question is, what is this velocity? What is this velocity? So we have to choose our system. Now, what system do you want to choose? I want to give that choice to you. We have time to do one system. So I want you to choose whichever system you want me to solve. Which object are we interested in here? We're interested in the train. So we probably should include the train, right? You cannot say, again, my laptop. Well, my laptop is not the choice of system here. It's irrelevant. We need to talk about the train. And on top of that, do you want to include the spring or not? Anybody have a preference?
Yes.
Okay, you want to include spring. Let's include spring. So train plus spring, we'll do that. And all right, initial moment, identify what is our steps. First step is choose your choice of system, right? Second step, initial moment, and final moment. We have already established it. I've already drawn it on our picture. And third part is to label all of these different energies. Sorry, in first and then out. So what is the final energy of my system, train and spring together at the final moment? What kind of energy they have? Do they have kinetic? Yes or no?
Yes.
So finally, you have already stopped the train.
So shouldn't that mean there's no kinetic energy because we're trying to find the maximum initial speed so we can safely get to 0?
Yes, so safely get to 0, which means at the final moment, then there is no velocity. The velocity is 0. So this is implicit in the problem. Okay, it doesn't spit out for you, but we have to know what information to read. So no kinetic energy. Do we have any other form of energy? Do we have gravitational? Do we have elastic energy from the spring?
We have elastic energy from the spring.
Elastic energy from the spring, perfect. And still, do you still remember the form? It's 1/2. What else is in there?
K change in x squared, but the change in x is the only thing squared, not the k.
Yes, okay, that is all. Our initial energy of the system, train and the spring, right here. So the initial moment is the train coming in and it hasn't touched the spring yet. At that moment, the train and the spring together, what kind of energy do they have? Do they have kinetic? Yes.
Yes.
That's just from the train. The spring right now has no energy, hasn't been compressed, so you do not have a potential energy at the initial moment. So it's really just a transformation from all that kinetic gonna go to your elastic potential. Because we did not talk about, we ignore friction, so you're not gonna have an output. Friction is always gonna give you an energy output, okay? The inputs is also 0 because now the spring has no, the engine is turned off. It's just being stopped, right? So you're not making it speed up. So there's no inputs. You put everything together, the equation is actually looks pretty simple. It's just 1/2 k delta x squared minus 1/2 mv squared is equal to 0. So you want to solve for v. Okay, you want to solve for v. Now x is given, m is given, is really just the k is not given. But that is where this little extra information comes in is, oh, this is just giving me k. Okay, so we're gonna do a little, carve out a little space to do the k here. So this is using Hooke's law. I know that this is k delta x, right? The force it provides is k dot x. And this force, according to Newton's second law, is equal to mass times acceleration. And the acceleration is given. So I know that k delta x is equal to m times g over 2. So this little bit of information is really telling me what the spring constant is. K is mg over 2 delta x. Now you know m, you know g, you know delta x, just like you know all these different terms here. So you could plug this in here and solve for your velocity. So the final result is the velocity is square root of g delta x over 2. And then you can plug in the numbers. Now, if you use feet, you will use 32 feet per second square for g. And you can keep your delta x as in 3 feet. So but you don't have to. You can say, I don't like to work with the weird units. I'm going to change feet to meters. I want to work with SI units, and then you can simply look it up. What is the feet to meters? And then you can plug in the delta X for that. And you can use your G for 9.8 or 10 meters per second squared. Okay. All right. So that's all. I encourage you to do the same problem, but now choose the train as your system. You can get rid of the spring and then use the train. And in my notes, there will be solutions, but I want you to be able to try to do it on your own first. Okay. All right. So that's all for today. I will see you Wednesday. Again, I wanted to make sure you guys take a look at the partial credit announcement on the Canvas. If you have any questions, let me know. Bye, everyone. I will see you on Wednesday.
I'm sorry, Professor. I kind of cut off. What did you say? The system was that was going to be provided, and so that we can check with your answer.
Oh, I will provide the solution for the train system, train without the spring. But
Okay.
you want you to be able to solve it yourself.
Right. Okay. Thank you.
Bye, Professor. Have a good day.
Bye. Have a good day yourself.
Thanks.